Hi, it is 10:57 p.m. I'm currently in Shanghai, and this is technically Linux running on CG3207. So how can I prove this? So the long story short is that this button here shows the program counter, which is one of the starting few instructions of Linux. And technically, if you scroll up to the very top, so this is generated through an emulator of what program counters run through Linux. You can generally see BC. So yes, technically, theoretically, this is Linux running on CG3207. As for how it's running, not so good. But technically 1 megabyte of Linux is loaded and running on the Nexus board's cellular RAM. So the Nexus board has 60 megabytes of cellular RAM. We have the CG3207 CPU on this Arctic 7 FPGA chip, interfaces through the cellular RAM with cache. The cache is a direct associative cache, so I can't remember exactly how associative it is, but it basically allows us to use the full 16 megabytes. Generally, we compile Linux through build root. With the help of a guide online, I've tried to optimize Linux to be as small as possible, and the most optimal size of Linux I got it to is 1 megabytes. 1 megabytes with no print K support, with no built-in UART support, and the only program it runs is supposed to be this. So it's supposed to print to UART somewhat through the memory addresses, and it's supposed to like control the 7-segment display. But clearly, yeah, so that's what it's do. So we have a simple init. What this simple init compiles to init ramfs. This init ramfs, we can incorporate it through build root into our Linux kernel image. Our Linux kernel image that I compiled is around here. So this is the Linux kernel image. And afterwards, so with the help of the mini RV32 IMA emulator, I've tried to basically get it to somewhat run. Okay, right now, if I try to get it to run, it's gonna give me a lot of garbage. So let me just comment out all the program counter stuff. Let me check if there's a printf. Yeah, there's a printf. So let me just comment that out. This is a modified version of the mini RV32 IMA emulator. The main reason why I modified it is so that it is small and it's basically small and simple to be used. Okay, let me just quickly fix this. Yeah, so now I can compile it, and to show that that Linux technically works, this Linux image is a real Linux image, kind of, and that this init runs. So yeah, you can see technically it prints out. It doesn't print out the whole thing because I set the Linux emulator to stop after it printed out like the exclamation mark character. But yeah, this Linux image is a real Linux image. It does run. It does what it's supposed to when it works. So now the next thing is that after we compile the Linux image, we need to handle the device tree. The device tree is basically the standard device tree. On the CG3207 CPU, there's a weird trick that we need to do, but I'll get to that later. I tried to strip it as much as possible. For now, because we are using direct memory access because there's no MMU, we can afford to like do all this kind of fancy stuff. And basically, I didn't bother to touch it, and theoretically, it should work on the CPU. So after I compile this, the way firstly that I get it to work is that because the CG3207 memory map, it doesn't start from 800000. It starts from like somewhere in the middle. So we'll need like a 0-stage bootloader to load all the instructions. So first we load the DTB offset, which is we fixed it at this, and then we load the RAM offset for Linux, and then afterwards we jump. So this loads at about like 00400000, and then afterwards it then jumps to the first memory location in Linux, and then it just runs. So yeah, so this is the process of how Linux is gotten onto. This is a process of how the Linux image is gotten onto the board and programmed on the board, and how the board loads it. As for how it's programmed, the CPU we have has a built-in extra CPU call for bootloading. So we implemented a speed loader that allows us to program the CPU. However, because of various design considerations, we only managed to get it such that it takes 2.5 hours to program 1 MB, which is quite sad, honestly. But it's due to a design consideration. It can probably be optimized by like direct loading from UART without any sort of feedback, for example. So now this is Linux because it does pass through the memory address. I've set a WFI here around here to make sure that it stops to show that we are indeed following the correct program flow. We are indeed running real Linux assembly. The problem with showing the rest of that is that the rest of it doesn't actually work. It crashes at about the 300 instruction. So it crashes somewhere around here. I think it passes here actually, but it passes here actually, but it doesn't crash. But at the very least, you can see that jumps do work. CSR instructions do work. I'm not sure if it crashes on Atomic's instruction, but so far it looks like on my own testing, it looks like they somewhat do work. So the part of the Linux kernel does work in some cases. It's just that you have about like 50,000 instructions between us and running in it. So yeah, this is technically Linux on CG3207, Linux 6.5.2 on CG3207. It technically runs. It just doesn't work.